All right, and then I'm going to share my screen. We'll give it one more minute.
So you're just waiting for people to join, or?
Yeah, so if you look at the bottom of your screen, you can see the number of participants, right? So it's like 27 right now. So we'll wait till around closer to 50, 40, 50.
But so you can also see the names, right? Yeah.
Okay, so I think the number of participants actually seems to be steady now. So I guess let's start. All right. So hi, everybody. Welcome to Polaritonic Chemistry webinars. My name is Matthew Du. I'm a grad student at University of California, San Diego in the group of Professor Joel Yuenzo. I will be your host for today's webinar featuring Dr. Claudiu Genes from Max Planck Institute for the Science of Light. Before we get started, let me share a few announcements. The Journal of Chemical Physics has a special issue titled Polariton Chemistry, Molecules and Cavities in Plasmonic Media. Submissions are now open and the deadline is October 16th. They welcome both experimental and theoretical works and any of the numerous topics within Polariton chemistry. For more questions, visit the jcp.aip.org and go to the upcoming special topics section. Next, here's the schedule of talks. So remember, it's every Wednesday, 9 a.m. Pacific Standard Time. And for each talk, register at this link. Last week, we had our very first postdoc spotlight featuring Dr. Bing Gu from University of California, Irvine, and Christine Anderdotier from University of St. Andrews. Next week, July 29, we'll have Professor Javier Esperua from Center for Materials Physics. And then on August 19th, we'll have our second postdoc spotlight. Future talks will be announced soon. So here's a few more details about the postdoc spotlight. So remember, it's 25 minutes per talk and then 2 talks. And then we thank everyone who submitted applications to present at this special event. And out of all applicants, 2 will be chosen by online popular vote. Today, the voting link will be sent out by email and social media, so keep an eye out on your inbox. Next, if you haven't done so, please check out and join the online public Facebook group called Polariton Chemistry Online Community. This is a central location where future webinars, new papers, conferences, job postings, and more related to Polariton chemistry will be announced. Also, this webinar series has a YouTube channel where you can watch and rewatch previous webinars. If you haven't done so, please subscribe. Now I'm going to go through the mechanics of the webinar. So at the bottom of your screen, you'll see 3 buttons: chat, raise hand, Q&A. Chat, you use it when you just have any questions or comments for the host or other participants, or you just want to have a discussion, and just type it in anytime during the talk. And then, yeah, so then raise hand is if you want to ask a question during the talk, you just click raise hand at an appropriate time. I'll have the speaker pause. I'll unmute you and you can ask your question. The last option is Q&A. So if you have any questions, you can type it in there. And then at the very end, the question will be addressed. All right. So now, let me introduce today's speaker, Dr. Claudiu Genes from Max Planck Institute for the Science of Light. Dr. Genes earned his BS in physics at the University of Bucharest. Then he earned his PhD in physics at the University of Michigan with Professor Paul Berman, where he studied spin squeezing and quantum measurement in cavity QED. He then did postdoc at University of Camerino with Professors David Vitali and Paolo Tombesi, where he made major breakthroughs in cavity optomechanics, in particular the cooling and entanglement of microresonators. He then continued making important contributions at the University of Innsbruck, where he was first a postdoc with Professors Helmut Rich and Peter Zoller, and later a senior fellow and project leader. There, he worked at the interface of cavity QED and cavity optomechanics, and also made his transition to cavity QED with atomic and molecular ensembles. Since starting his own group at Max Planck Institute in 2017, he has been a leader in the field of polariton chemistry, developing new techniques of open quantum systems to study charge transport, energy transfer, and creative new ways to induce light-matter coupling. Without further ado, let me introduce Professor Claudiu Genes, who will be talking about quantum optics with molecules. Dr. Genes, the screen is yours.
Thank you very much for the kind introduction. I will just 1 second to share my screen. And right, so again, thank you very much for organizing these kind of online events, and which cannot really replace the real talks, but they're pretty good in that. And again, thank you for the introduction. So at the moment I'm working in the direction of quantum optics with molecules, and eventually I would like to go to the direction of real chemistry. At the moment, the only connection to chemistry is only descriptions of effects such as first resonance energy transfer, which for chemists is a well-known thing. But most of the stuff that I will talk today doesn't really have much to do with chemistry, except for the fact that we try to create some simple mathematical models for dealing with some simple molecules. So, and a main topic in my research is the question of quantum light-matter interactions in confined regions of space, which is what I call cavity, which are optical cavities, and this field is basically cavity quantum electrodynamics, right? So what I will talk today mainly is about cavity quantum electrodynamics with molecules. So I'll structure my talk in 3 parts, and I'll try to spend enough time on these fundamental concepts that everything else should be pretty easy to understand afterwards. And then I'll go to 2 different directions. One of them basically doing cavity QED with single molecules. So at the point in which we just create some simple models for describing the dynamics of these kind of systems, of light-matter interactions in these kind of systems. And later I will describe something that is not, we haven't completely done, but we are just going to this direction to scale up the interaction of light and matter to the level of many molecules. So I'll start with simply introducing what this cavity quantum electrodynamics is, just in very simple terms. So if I want to have a strong coupling between light and matter, then I need 2 ingredients. One of them is the matter part. And for this, I usually use these 2 notions, either quantum emitter or the simple version of a quantum emitter, which is a 2-level system subject to decay. And the other part is this optical cavity, which in the simplest case can be provided by just 2 parallel mirrors in which photons can bounce back and forth. Right? So we go to the first part of these 2 ingredients to describe quantum emitters as two-level systems. So that's a gross simplification for most systems, but it's a pretty nice mathematical model to describe light matter and interactions for atoms, molecules, ions, quantum dots, and so on. So mathematically, all we need is these two-level systems where we have an operator which we call which is two ladder operators. One of them that takes you from the excited state to the ground state, and one of them which takes you from the ground state to the excited state, right? This one, and you can see this, diagrammatically just as arrows up and down. And for these two-level systems, you have three possible processes. Two of them are just stimulated absorption and emission, in case you have a coherent light source like a laser drive. And you also have the ubiquitous spontaneous emission. The fact that any two-level system or any quantum system is in touch with a big bath, when one eliminates the big bath, one always ends up with some incoherent process. And this incoherent process for electronic transitions is just radiative emission into a dipole pattern into free space. And that's what we describe by this rate gamma. Now, going on the second part of this cavity QED, so the discussion, the concept of confining light modes. Imagine just the standard Fabry-Perot design where you have two parallel mirrors, and if I think about photons, I can think that photons are recycled by scattering back and forth from the mirrors, which increases a lot the interaction time with a possible quantum object inside the system. On the other hand, even if I look at a classical picture of this platform, I just imagine that I send some light plane wave, and I can see that the electric field per photon or per quantum of energy is strongly increased, right? So the picture here is realistic. So the electric field amplitude is much larger inside if I hit one of the resonances of the system. And the important thing is that these kind of systems have a lot of resonances. In the ideal case, they are equally spaced and they have a Lorentzian profile. And the Lorentzian profile corresponds to the fact that the mirrors have some loss. So they're not perfectly reflective, but they allow photons to escape, which means any resonance inside such a cavity has a Lorentzian profile describing this loss with a line width of this kappa. Right? Good. So if I look at any of these quasi-modes, I can, because they are so spaced, they're so far from each other, I can always describe a single mode problem where I simply quantize my Hamiltonian. I write a Hamiltonian, which is h bar omega c corresponding to this individual frequency that I pick, and an a dag a, which simply counts for, it's a photon number operator, right? And a's are just typical bosonic operators. Good. So now I put this quantum emitter together with the single confined optical modes, and I can write a Hamiltonian which conserves excitations. It's obtained under some conditions as a simple form of the Rabi Hamiltonian. And this one basically tells you that you have a photon number operator that counts photons. You have an excitation sort of operator that tells you if the excitation is up or down. And you have an energy excitation conserving term that describes exchange of excitation between the field and the system and the quantum system. So at the individual points, either the excitation can be either in the field or in the field mode or into the two-level quantum system. And if I were to look at the eigenstates of this Hamiltonian, I would get two different eigenstates. If in the simplest case, when the cavity and the two-level systems are resonant, then these eigenstates go plus and minus g with respect to the common resonance. And I immediately can find this by just simply scanning the cavity input port. And I would find that the transmission of the cavity, instead of being a Lorentzian corresponding to a simple resonance around the cavity frequency, is split into two Lorentzians corresponding to two different possible polaritonic states. And these polaritonic states, which are hybrid light matter states, they are simply superpositions of two different possibilities. Either the excitation is in the two-level system, and there's no photons in the field, or the excitation is in the photon field and the two-level system is not excited. And the upper and lower polaritons, so the two different polaritons are which are separated by which are positioned at plus g or minus g with respect to the cavity resonance, are corresponding to the two possible superpositions of this, so the plus or minus sign. Now, why would anybody care about this kind of system? Well, first, because it's a coherent light matter interaction system. So you can have a coherent rate of exchange of information between the two systems, which is this G, which is larger than the loss rate. So these are the bad rates, the rates that take the information away from the system. And also because they could be useful for optical devices, as nonlinearity is already expected at this level of the single quantum emitter level, and you can get something like a photon blockade effect. Now, if you were to do an experiment and you didn't bother of getting a very good cavity and a very well fixed two-level system, you can also reach this strong coupling regime at the level of many quantum emitters. And in this case, you emitted a lot of, you imagine a lot of quantum emitters inside the cavity mode, and you write the Hamiltonian, which is a bit different, which in the simplest case, that all the emitters would be coupled with the same rate. It's just a collective exchange interaction where the excitation can either be into the photon field or into a quantum superposition of all these quantum emitter states. And this collective strong coupling condition reads like this: is G squared of n is larger than all the loss rates in the system. And it still gives you some advantages, that you have the coherent light matter interactions. As you've probably seen in a lot of these seminars before, you see that such collective strong coupling effect can also allow for the modification material properties. So allows for, let's say, vacuum modified chemistry, for example. But it has, from the pure quantum optics point of view, it has a disadvantage that it has very weak optical nonlinearities, and one cannot implement, for example, the photon blockade. Good, so that's the first part of the introduction, going to this cavity QED. The second part is, what do we mean by molecules in my language? So when I think about molecules, I think about the simplest one, and I know that anytime I look at the electronic orbital, the orbitals depend very much on the arrangement of the nuclei, right? And also know that the nuclear vibrations influence the absorption emission spectra a lot, which means that one has to take into account nuclear vibration, right? So the two-level system, just electronic orbitals, is not enough, a good enough model. So I like this representation because that's how one understands how this bond is made in a hydrogen, the simplest molecule. You look at the hydrogen molecule, you see how the nuclei, they come together, and suddenly the electronic charge arrangement favors a given distance between the two nuclei. So if I look at the molecule in general, I can identify along the nuclear coordinates, so the distance between the two nuclei, I can identify a potential landscape for the ground state and the excited state. In the simplest approximation, I can consider that these are simply just harmonic. So one can start immediately from first principles and see that well, I can simply just write a typical Hamiltonian, where for electronic degrees of freedom, which are given by this projector operators into ground and excited state. That's the projector operating to the excited state. That's the projector operating to the ground state. And I simply expand my potential around this in a harmonic expansion. And I add to this the kinetic energy of the center of the relative motion of the two nuclei, because the center of mass of the two nuclei doesn't really care about this. So I do this expansion of the molecular potential landscapes. I take the harmonic approximation, and in some molecules, there's a big difference between the minima of the excited and the ground state potential, which introduces this electro-vibron coupling. And a very simple calculation where one quantizes the motion. So simply you replace the R and P, because you have harmonic potentials, with P and B dagger operators. So bosonic operators that take you up and down the vibrational state ladder. So if you do this, you identify a term which is called the Hwan-Ries factor, and depends very much on the difference between the two minima, and you end up with the Holstein-Hamiltonian. So Holstein-Hamiltonian tells you that you have a harmonic oscillator for the motion degree of freedom, so for the relative motion of the two nuclei. You have a slightly shifted frequency difference between the two electronic orbitals, and you have a coupling which is displacement times excited state population between the vibration and the electronic degree of freedom, and that's what one describes as a Vibronic coupling. So I take this Hamiltonian, and it's pretty trivial to see how this is diagonalizable, and this is well known in condensed matter physics because it describes electron-phonon interactions in a solid state. So one can perform a unitary transformation, which is simply what I call a conditional displacement. So you perform a displacement, which is just a normal displacement that everybody knows from quantum optics. You displace the vacuum into a coherent state by this operation. So you take a displacement that only acts if the eigenvalue sigma dagger sigma is non-zero. And sigma dagger sigma is zero in the ground state and is non-zero in the excited state. So this is a conditional displacement, which when applied to the left and right to the Hamiltonian gives you the modified Hamiltonian, the displaced Hamiltonian, which now is diagonalizable. So this is in the diagonal form, and the eigenstates are simply eigenstates of the B dagger B, which is just occupancy number, and in the Fock space of the B dagger B of the vibrations, and you index this with the excited state or ground state of the two-level system. So now I come to the end of my fundamental concepts, because everything that I will talk about is deals with quantum Langevin equations. So I just do a very simple transition from master equations, which I assume most people know. So typically, if I want to write an equation for an open system dynamics, then I can, it's an extension of the Schrödinger equation to include the losses from the system. So this is written as a von Neumann equation for the density operator of the system, and to which one adds losses in a Limblad form. So if I look at this, Limblad form, it just simply tells me that I have a collapse operator, so something that takes excitations away from the system, so it goes down, and this excitation can go away at the loss rate kappa. So I just need to know the collapse operator and the loss rate. And one can actually generally translate this to quantum Langevin equations. So for any operator O, then I simply have to write this kind of equation where for any channel in which I have a collapse operator A, I have an equivalent input noise, which makes sure that, which is correlated in such a way to describe this kind of loss. And I just want to give you the example of the Brownian motion. So think about the pollen particle, which I kick, you can kick from all directions with the water molecules. And if you don't want to describe the whole universe of many, many, many molecules, water molecules and the pollen particle dynamics, you can average over the kicks, and you end up with an equation that tells you that the momentum is changed in such a way that you have some Stokes damping. So you write something like P dot equals minus gamma P plus a noise term that accounts for this damping. And this is what you know as fluctuation dissipation theorem, that for any dissipation process that you have, there's got to be some fluctuations that when correlated gives you the dissipation rate. So for a single undriven cavity mode, and since we're going to consider cavity modes, for a single undriven cavity mode, one can use this formalism just immediately to derive an equation for the cavity field operator. And you can find that the cavity mode simply decays at the rate kappa. It evolves at natural frequency omega c, and it has an input noise, which typically is correlated in such a way to give you a frequency, a flat frequency power spectrum. So if I Fourier transform this thing, I would get a power spectrum which is flat. Good. So these are the introductory concepts. Should be pretty much enough to understand the rest of the talk. And I will start with this. Description of quantum Langevin equation for polarions. So the situation that we considered was initially single molecule inside the cavity, optical cavity, where I might have some noise coming in, or maybe some driving of the molecule. I might also have some driving of the cavity, and my molecule is modeled as a two-level system interacting with a lot of bosonic modes. And what I mean by this is that I have a single electron orbital that cares a lot about how the nuclei reorganize inside the molecule. So I can consider a molecule which is big enough, but I only look at the one electron orbital, and then I assume that on each nuclear coordinates, the nuclei can vibrate in different ways. Sorry, for each, I assume a lot of nuclear coordinates, and for each of them, there's an individual vibration, which is described by this harmonic approximation of a bosonic mode. And these are just the Hohenriechs factors, which one could eventually read from some table somewhere. So we take the system, and what we want to do is find an analytical approach to these molecular light interactions, and And ideally, we want to include any kind of number of vibration degrees of freedom, because if one had to do this numerically, this would be an amazingly complicated task. And ideally, and finally, what we want to also do, what we wanted to do, is to translate cavity quantum electrodynamics concepts such as strong coupling or Purcell effect to molecules. So how do these things modify? And the task actually was not too hard, especially that this is basically a approach which is very similar to what has been done in optomechanics for single photon kind of interactions. The mathematics is sort of the same, except that one replaces bosonic operators with spin operators. So this sigma operators actually, which we call here polarons, the sigma interacting with the bosonic vibrational mode, is in the case of the optomechanics is basically just a bosonic mode of a cavity interacting with vibrations of a vibrating mirrors. So a very simple description of what these equations actually mean, and these equations are only obtained as a perturbative limit in the case of not such high excitations. So assume I have a molecule and I know the power spectrum of these vibrations. So I know exactly where the vibrations are positioned in frequency, and also know how they relax. So I take this system and I can write a set of equations starting from a typical Holstein-Hamiltonian that I write for many vibrational degrees of freedom. And I can include the input noise of any vibration as a thermal reservoir. So I have these kind of correlations, which are typical for a thermal reservoir, and I assume a thermal occupation of the vibrational mode. And just to mention, so why do vibrations, for example, relax in molecules? One would typically have two paths. So one of it is because molecules are pretty big and they're also a bit nonlinear. So each vibrational mode could couple to a lot of other vibrational modes inside the molecule. And that's what I would call intramolecular vibration relaxation path. And the other thing is that typically molecules are in solvents or in solids. So any kind of vibration of the nuclei would interact with the surrounding bulk. Right, and ideally one would consider that this is really a thermal equilibrium problem. So a thermal reservoir kind of description for the input noise would be a good model. The second equation describes the evolution of the polaron operator. So we don't describe just the electronic degree of freedom, but we address the electronic degree of freedom with the displacement with actually a product of displacements along all nuclear coordinates. And this is basically just tells you that the electron is sort of, you follow the electron plus all the vibration along all the nuclear coordinates. And this is the proper operator to follow. And finally, one can have an input noise that comes from radiative emission, so from spontaneous emission. And under some assumptions, this can be written like this: is just an input delta correlated input, zero average input noise, plus some classical drive that could be a laser that one shines on the system. So what we want to find basically, what is the response of this system, assuming that we have a resonance, electronic resonance, we have the coupling to the vibrations, and we have this omega laser, which we can scan. So the equations have a very simple solution, which just basically tells you that, I mean, all you have to do is just integrate, find the homogeneous solution, you integrate this, and you find two parts. One of them is the transient part, which tells you how the system evolves in the short time scale. But notice that as soon as you go to time infinity, this term goes away. And if you go to larger times, you have this apparently complicated term that describes the steady state of the system only for the electronic spin operator. So what do you do with this?
Dr. Genes?
Sure.
We have a question?
Yeah.
Okay, go ahead.
Yes, Gilad Ran. I have a question about the equations that you showed. Are these, perhaps I missed it, are these completely phenomenological, or do you can derive them from some first principles?
These are completely derived from the Hamiltonian of the system. So one writes the Hamiltonian for the electronic degree of freedom, the Hamiltonian for the vibration degree of freedom, and the Holstein Hamiltonian, which I've shown in the fundamental concept part, which shows you the interaction between sigma and all the B's.
Okay, thank you.
And the second part, the input noise, one can simply derive by considering radiative emission and the vibrational relaxation for the vibrations. And the path to do this, the simplest path to do this, is that master equation translation to quantum Langevin equations. Okay.
Continue.
So how does one calculate anything after this? So first one can take this expectation value of operators, and I only consider the steady state, so consider the transient already went away. So you see that the important quantities are these 2-point correlations in time of the displacement operator, and you would probably find these kind of calculations in any textbook quantum optics, textbook. And notice that you need to correlate the operators like this. And to do this, one simply calculates the steady state of the B operator for the vibrations. And again, this is just a simple formal integration of the equations that I shown before. So the B operator follows the input noise and with some convolution. And we only consider, so one gross simplification is that vibrations relax pretty fast compared to anything else. And I think this is known as Kashar's rule, right? That once you go up in electronically to some upper vibrational state, this usually goes down pretty fast. So if you consider only the steady state for vibrations, we can see that the correlation, the 2-time correlation of displacement operators just gives you an exponential that we can expand in these kind of terms. And notice that this is just a Poisson distribution, right? And this simply corresponds to the Frank-Condon principle. So this gives you exactly the kind of, depending on the kind of transitions you do, it gives you a Poissonian distribution of probability of actually getting there. So similarly, from this equation, one can immediately get to the absorption profile, where it's not exactly the absorption spectrum, but it's the absorption profile, meaning that what is the population of the excited state as a function of the input power of the laser and as a function of the laser frequency. And notice that if I didn't take any vibrations, so I say that my vibrations were completely decoupled, I would only get a Lorentzian. So this would be a typical Lorentzian profile of an atom, right? In an atom, you don't have any coupling to vibrations. Now, by computing, so in order to compute the absorption spectrum and the absorption and the emission spectrum, one ends up with these 4-point correlations, and that would make my talk pretty boring if I had to go through that. I mean, more technical than this. So if you calculate 4-point time correlations of these displacement operators at different times, one can end up with a whole emission spectrum, which looks pretty much like this. And you can identify here from this formula, for example, you can identify, for example, the second peak in the absorption spectrum. It lies to the right of the transition frequency. So it's correct that you have to absorb more frequency, so more energy. So you can identify here that the omega laser should be omega of the transition, of the electronic transition, plus 2 times nu, so 2 vibrations. And you can also see that the 0 phonon line is lifetime limited, so only has a gamma, while any other lines in the absorption spectrum afterwards acquires a much bigger line width because of the vibrational relaxation. And this also makes complete sense. If you look at the lines, you always see that each line can go down either because of vibrational relaxation or because of radiative emission. So to sort of conclude this, all I want to show is that if you start with this quantum Langevin equation and the sum approximations, one can actually get a lot of the features of the system, and one can translate to known effects like the Frank-Condon factor, the absorption profile, emission profile, and all the Poissonian distribution and individual features like line width, radiative line width, and non-radiative line width. Good. So now we basically, this kind of part of our derivation was just to sort of show that everything makes sense in this formulation. But then we applied this derivation to a cavity filled with molecules and tried to translate a few concepts that one would usually derive with two-level systems, or would understand with two-level systems, to molecules. So we can write the same kind of Langevin equations by assuming a system where we have a driven cavity So a cavity is driven from here. We just want to look at the output. And we, for example, want to calculate the transmission of the cavity. We want to see what the polaritons are peaked. And want to see if the polaritons really are an eigenbasis of the system or they make sense. So without going into detail, we calculate also, I mean, we do, the only tricky part is that one has to displace. So one has to address not only the electronic degree of freedom, but also the photonic degree of freedom. And then one ends up with this very simple system of equations, which can be solved by just diagonalizing an evolution matrix of the system. One finds a different eigenvalues, and these eigenvalues now should correspond to the polaritons, and with some some matrix that diagonalizes this evolution matrix. So there's an expression, you don't have to look at it. What this expression basically tells you is that if I had a molecule which was perfectly symmetric, meaning that the electronic orbital in the ground state and the excited state would be exactly the same position, so the nuclei would not have to move to be displaced, then the two polaritons would be perfectly symmetric with respect to the cavity frequency. If, on the other hand, I have a vibronic coupling, what I notice is that the polaritons are also, one of the polaritons is reduced, while the other one is very much wider and very much reduced in the amplitude. And this actually comes from, so one can derive this perturbatively. It comes from an effective loss rate from the upper polariton to the lower polariton. And this has been an effect discussed also in theory by Javier Espurua and Thomas Neumann, and also these are effects that have been seen experimentally, right? And we looked at a few other. So if you check out the paper, you see there's a few other processes that one can derive analytical solution for, including the first resonance energy transfer between two molecules in the cavity and outside the cavity. And all of these have very nice, one can obtain very nice analytical results where the physics becomes pretty clear.
Dr. Genes,
Sure.
We have another question?
Yeah.
Okay.
Hi. So I have a question regarding your formalism. So if you use these Langevin equations, is it possible to describe this limit where you can, in the very, very strong light matter coupling, where you can change Frank-Condon factors? So you can describe something like that with these kind of models? Or do you have?
Let's say at the top of my head, I would say at the moment, no, because we make this approximation that we never drive too hard.
Okay.
So we have a linear sort of response of the system. So for a two-level system, if you drive harder, I mean, if you put too much saturation, then you will get to the point in which the two-level system might give you a current nonlinearity and then more and more as you go towards saturation. So I would say that if you need to use high intense laser pulses, then the formalism, at least the way we describe it now, it does not work.
Okay, so what you're saying is that you will need to consider like higher order correlation functions if you want to describe.
And everything. So what we can actually solve is based on the fact that our approximation allowed to linearize the system. So we have exact solutions, meaning that the system evolution is just going to depend on the initial fluctuations plus an evolution matrix. And in that case, would be a nonlinear system that analytically, is hard to solve.
Oh, yeah, I see. Thank you.
Okay. Okay. So just as a note, so I will not talk, since I don't have much time, I will not talk about what I actually really intended to talk in the second part of my talk. Just as a comment that we actually was very happy to take all this Lindblad formalism for the vibrational relaxation. So what we assumed in the beginning was that vibrational relaxation occurs as a normal Lindblad term, where you have a collapse operator that just takes the number of vibrations, takes you down the ladder of vibrations. And we noticed that this gives actually wrong predictions for the zero phonon line at finite temperature and close to zero temperature. So typically it's well known that the zero phonon line is lifetime limited, close to zero temperature. And what we found is that there's some sort of dephasing. And we checked, if a Brownian noise model actually gives better results, and this is actually true. So Brownian noise model cannot be written in terms of mass equation as a Lindblad mass equation form. So in order to do this, we started from first principle and say, well, how do vibrations relax? And one of the mechanism is they relax by emitting energy into a crystal, so into vibrations of a whole crystal, so what we call phonons. And we solved the problem where we have a cavity where one now positions a bunch of molecules inside the crystal. And if you look at the diagram of interactions, so now basically we have a two-level system, which is the electronic degree of freedom, interacting via the Hwan-Gries factor with the nuclear vibrations in the system. But the nuclear vibrations, when the nuclei are displaced, they can also displace the whole crystal, which means that the nuclei are connected to all the phonons of the crystal. On the other hand, the phonons of the crystal, so the vibration of the whole lattice, can also influence the electrons, so they can shift the electronic orbitals. And on top of this, we couple light directly to the electronic degree of freedom. So we looked at this kind of problem and we found a few nice, interesting effects. First, we checked that you get all the Debye-Waller physics, so phonon wings on the emission spectrum. And also we checked that the vibration relaxation model that we obtained from this has two features. It can be either non-Markovian or Markovian, depending on the phonon spectrum. And indeed, the zero phonon line prediction, so the zero phonon line problem was not there anymore. So, but as I said, I would like to give a more, instead of going through all the mathematical details of this, I would just let you, check out the reference. And I will move to something else, which is also inspired by optomechanics. So in optomechanics, there are very interesting effects which come from quadratic interactions. And one can immediately see that if I consider the typical molecule, for a typical molecule, we always say that we obtain this Holstein Hamiltonian by doing some displacement, and by just displacing the potential surfaces. They are both harmonic, but they have the same frequency. If, on the other hand, somebody assumes that the frequency in the excited state, so I take two potential surfaces. Typically, I have a Morse kind of potential that I approximate as harmonic. And if I consider that the upper potential landscape is a bit tighter than the lower one, then if it's tighter, it has a higher frequency. And if I calculate from first principles again the Hamiltonian, I get the typical Holstein term, so the typical vibronic interaction, plus another term which scales like p plus b dagger squared. So it's a nonlinear problem already. I mean, it was already nonlinear before, but now it's nonlinear in displacement. And if I look at this coupling, is actually pretty small. It scales like the frequency difference over the frequency of the harmonic trap. But it also allows for analytical solutions. And this is what I want to point out in a few words, that what one needs to do now is not only a conditional displacement, but also conditional squeezing operation. And these are typical displacement and squeezing operators in quantum optics. And if one tries to diagonalize this Hamiltonian, then one can immediately find the new parameters. You notice that the displacement goes like lambda 1, so the Hwan-Gries factor over 1 plus 4 lambda 2. And so if there's no difference in the traps, we reproduce the original vibronic coupling. But then on the other hand, the squeezing, so the squeezing part gives you, what kind of squeezing operation one has to do. And this is the diagonal form of the Hamiltonian. And what we aim, so this is a work in progress, what we aim to do is to see, can one modify the emission absorption spectra of a molecule by just doing a very smart potential landscape engineering? And then the second question is also how to do this potential landscape engineering, of course. And then the second thing is that can one really take advantage of this light matter interface by eliminating the electronic degree of freedom and formulating the problem as an optomechanical problem. So mapping states of light onto motion of nuclei in a molecule and the other way around. So eventually using this asymmetry, this difference in the potential landscape curvatures to produce mechanical squeezing, to produce squeezing of light. So mapping the mechanical squeezing into light squeezing. Good, so this brings me, and I think I'm pretty much on time. unless the moderator says I'm not. So I still have 10 minutes for the last part.
Yep, you're good.
Okay, so now I want to talk about a few things, which is again mainly work in progress, about quantum optics in many molecules. And if now I write this Holstein kind of Hamiltonians, I assume that each molecule is a two-level system describing the electronic degree of freedom, coupled to a multitude of vibrational degrees of freedom. And then maybe I also have disorder and everything else in the system. The problem, if I want to simulate the problem, becomes pretty much impossible. Right? So some smart analytical methods would always, in principle, be necessary. So we are looking we are looking at the complete problem, at least identify some important aspects. So one of them is typically molecular ensembles are not like the atoms in optical lattices. They're not far from each other. They're actually within a few nanometers. So that puts them, for any kind of normal density molecular ensemble, that puts them at the point in which you have near field coupling. So there's strong dipole-dipole interaction between. And if in principle, so this would be for molecular, for this typical organic molecules. And on the other hand, also if the density goes even farther, even higher, I also expect that electronic charge transfer is going to take place there. So we considered this assumption that we have dense molecular ensembles, but without electronic charge, without electronic migration. We considered disordered ensembles, which should be the typical case, since you always have inhomogeneous broadening. And then on top of this, we consider Vibronic coupling and near field coupling. So the first effect that one expects is that since some of the molecules are because of disorder, some of the molecules are very different in frequency from other molecules. If they find each other very close to each other, I would expect that the FRET, so first the resonance energy transfer process, could actually take place. So I can split my ensemble into blue kind of colored and red kind of colored molecules. So some of them are fitting the donor kind of profile, some of them are fitting the acceptor kind of profile. And if I combine Vibronic coupling and near field coupling, this is how I get a FRET process. And I will explain some slides. In 2 slides, I will explain exactly what I mean by this FRET process and how it goes. But now I just want to ask, so the kind of questions that we ask now is, one of them is, so taking all these things into account, how does the vacuum-Rabi splitting scale with increasing densities in the ensemble? By just taking all these possible aspects into account. And the second one, which is a bit more complex, is if I look at the vacuum-Rabi splitting in a typical cavity QED scenario, I can obtain this very easily by just mapping all my physics into a bunch of coupled dipoles or a bunch of coupled harmonic oscillators. Right? The vacuum-Rabi splitting simply tells you that you have a G-squared event that comes from coupling a single mode to a lot of other modes, but it doesn't really have anything quantum in the derivation. So one of the questions that, since we always, principally people always talk about macroscopic states where quantum superposition of many molecules, the question is there a direct connection and is there a measure that connects this vacuum-Rabi splitting as an observable effect to a real macroscopic quantum superposition states of many molecules? And I will tell you a bit more about this, but first, just some results which are actually pretty well known from the literature. There's some papers from the 90s that describe what happens when I have a disordered ensemble and I wanted to look at cavity QED physics. So consider the cavity and you do a transmission, you measure the transmission of the cavity, and the cavity is made by many molecules, and if all of them are coupled the same way, you get typically a G-squared of n kind of splitting between the two polarities. But now if the molecules are not the molecules, but if the two-level systems are very disordered, what one observes is that there are some collective states which give rise to different kind of resonances in between. And if you do a bit of the math here, writing all this, so writing the equations of motion for the cavity field and collective states of the system, and these collective states of the system are obtained as either bright state, and what I call a bright state is the state that actually couples to the cavity field, and states which are orthogonal to this bright state, so which we call the dark state. So if you look at the dynamics of the system, you see that one can actually identify the strong coupling sort of part. So this is the part that I depict here, where the cavity field is coupled to a collective symmetric superposition of all the two-level systems, and then also coupling to the dark state manifold. And the coupling to the dark state manifold comes through these terms, which I actually just tell you, so I didn't define them here. They just tell you about the disorder distribution, so the disorder realization. So if there's no disorder, there will be no coupling to the dark state. So the cavity just simply tells you that you have two polaritons which come from the bright state interacting with the cavity field. If now I have disorder, then I start mixing bright state with dark state. So I start coupling them. And after a while, one can actually calculate analytically the condition that the strong coupling condition breaks down. So disorder already modifies the strong coupling condition. And then we looked at what happens if now include near field effects, because the density is very large, plus dipole-dipole interaction. And we came up with this Fret migration of excitation. So now I promise I explain what I mean by this Fret. So we assume that you have two molecules and they are different in frequency. So the frequency in which one of them is going to emit is different than the frequency that the other molecule is emit. And I put some light at the absorption peak of the donor molecule. And according to Kasha's rule, this vibrational relaxation is really fast. So immediately I go into the excited electronic state of the donor. Now, since the molecules are close to each other, they can dipole-dipole interact. And this would be a resonant interaction, which means the excitation could go into the acceptor, but it has to go somewhere in the high in the vibration manifold. And assuming there's plenty of states in this vibrational part, then I could have a decent transition probability. Afterwards, of course, there's an incoherent, there's a unidirectional vibration relaxation, and then I get the emission at a different frequency. So typically, this is what one would do. One would use in order to measure the concentration of some acceptor molecules by modifying in a controlled way the concentration of the donor molecules, because then the distance gets modified by the distance gets smaller, the near field coupling gets larger as the concentration gets higher. So what we could obtain from the other formalism that I described before is that one can actually calculate an effective Fret rate as an incoherent process where an electronic excitation goes from a donor to an acceptor-like molecule. One can in principle calculate this analytically just as a sum of different kind of possible processes. And if you look at this expression, in the end is that if you sum over many vibrations, it's exactly what is known as an overlap integral in this Fret community. So basically we sort of calculate analytically an overlap integral for the discrete case in which the molecules don't have too many vibrations. And then if we include this rate phenomenologically as a loss of excitation from some molecules in the ensemble to some other molecules in the ensemble, then we can get a scaling of the vacuum Rabi splitting that shows that it's not exactly square root of n as the density goes larger, but it's actually something which saturates as the Fret migration starts sort of destroying the coherence in the system. So this is still work in progress. As I said, we are only able now to do simple numerics, but we intend to go to much larger number of molecules in the system. But it shows in principle that the combination of all these effects would affect the vacuum Rabi splitting that one expects. So whatever one measures as a vacuum Rabi splitting might be just some approximate number that has to take into account density, the vibronic coupling, and disorder. So this is my concluding slide. And this is again work in progress, which might or might not be relevant at one point. But we played around with some sort of measure of macroscopicity of quantum superposition state. And we defined something which we call this macroscopicity, which is basically a sum of our coherences in the system. So we look around basically how the excitations move around into a system. And we match this in such a way that for a W state, which is a perfect superposition of an excitation distributed around many, many molecules. So this would be again, this is a perfect quantum superposition state. If you calculate this macroscopicity, you get n. So one should read it as this is a state in which n particles participate fully to a quantum superposition state. On the other hand, if you take a state which is completely mixed, which you would get, for example, by putting thermal light on a bunch of molecules, bunch of two-level systems, the macroscopicity only takes the value 1. And this basically means that only one particle at a time sort of participates in a quantum state. So there are no real macroscopic quantum states there. So what we looked at how this measure is for example, so how this measure looks like when we take a cavity and we disorder the whole ensemble, we make the whole ensemble completely disordered, and we also eventually include vibrations. And we found that depending on the different, so independent on the initial states of the superposition, so you can either take a mixed state or a single atom excited or a W state, in the long run, the cavity sort of establishes a macroscopicity in the system. And this macroscopicity is not necessarily the number of particles that are in the cavity, but it's another number. So at the moment, this macroscopicity and vacuum rapid splitting might be very close to each other, but they're not exactly the same. They don't give exactly the same number. Good. So with this, I'm actually finished, and I would like to mention all the collaborators, and also to highlight that some of this work is done with together with Guido Pupillo, Johannes Schachemeyer, also locally with Diego Martin-Cano in Erlangen, and also it's a lot of this work has been inspired by discussion with Thomas Edison, and also that's at the level of many molecules. And also especially with Vahid Sandoktar, who's a local collaborator at the level of single molecule interacting with cavity fields. And the main work has been done by Michael Reitz and Christian Sommer in my group. And this is it.
All right. Let's thank Dr. Claudiu Genes for the nice talk. And now let's open the floor to questions. So does anyone feel free to raise your hand or type in the Q&A if you have any questions. If no one has questions yet, I'd like to ask a few questions. So, actually, one question. So let's see. Okay, go ahead, Luis.
Oh, yeah. Hey again. So I was, so in your work, or Fred, if I understood correctly, you were considering a static disorder in the equations of motion that you show, right?
So just frequency disorder, right?
Yeah, so static disorder. But so did you develop, or do you have any idea of what happens when you consider this dynamic disorder, like Vibronic type coupling in your?
So you mean the?
If you consider like high frequency in those equations, if you consider like high frequency vibrations.
These equations just describe the static disorder, as you say, so frequency disorder.
Yeah.
While here afterwards, we actually considered also dynamic disorder. So this is including vibronic coupling.
Oh, I see. Okay.
This is including vibronic coupling and also dipole-dipole interactions, so also high density effects. And
so when you include this vibronic coupling, you have additional like fast channels of relaxation to the dark states, right?
Exactly. So these are in terms of, so we didn't formulate in terms of dark states in this case. We found that if you look at each individual particle in the system, then the Fred migration of excitation adds to the natural radiative loss rate. So you simply have system, then you have to diagonalize your system, and you see that instead of getting the normal strong coupling regime, the strong coupling scaling, you would get something modified where some of the very donor-like particles, which are unhappy to find themselves a lot of acceptors around, are going to get out of the superposition because they're too lossy.
Right.
So it simply means, again, it simply means that instead of having many particles which all are not so, which are pretty not so lossy, which can come together to produce strong coupling, you have less particles. So you can actually see that the more you increase the density, particle by particle sort of fall out of the strong coupling condition. And that's why you can scale like square root of n and then square root of n minus 1 and so on. So basically square root of n minus, big donors.
Okay, thank you.
Okay.
All right, so now we actually have a question in the Q&A. If you want to ask your question live, please raise your hand and I can unmute you. And then otherwise, I can read the question. Okay, so I'm going to read the question from an anonymous attendee. So, and Dr. Genes, if you want to read the question too, it's just open the Q&A box. So
I can read it if you want.
Oh, you got it? Okay, cool. Go ahead.
Okay, so the question is the following. Let me just go to the slide. So that was the question of asymmetric polaritonic features. Right, so when you show the asymmetric polariton features in the presence of vibronic coupling, was that the vibrational origin of the electronic transition? Would the polariton states look different if you were strongly coupling a vibrationally excited state within the electronic excited state? So this is not, wait, I'm not sure I understand it, but this is actually coupling of a cavity to the electronic degree of freedom, and the electronic degree of freedom couples to the vibrations. While it seems that the question, refers to vibronic coupling to a cavity. So if I consider a molecule and I look at the ground state, then I can vibrationally couple to a cavity if I have, for example, an infrared cavity coupled to infrared active molecules. But in our case, we simply couple electronic degree of freedom to a photon of the cavity, and the vibrations just simply destroy. So the vibrations just destroy this coupling by coupling to the electronic degree of freedom. So I'm not sure I understand the question. Maybe if you can, if the anonymous attendee would write a bit more.
Yeah, feel free to also put it in the chat or raise your hand too. Okay, so I don't know. Yeah, I guess. Oh, okay. We have another question. All right. Go ahead, Raphael.
Hi. So I'm wondering, in the case where you have static disorder, if you looked at the emission spectrum due to dark states, and if you get Gaussian line shapes for those dark states, or the Laurentian, and how does that depend on the static disorder distribution? Thank you.
So if I look at the static disorder and I look at this, so I look at this situation where I have many two-level systems, and I look at the cavity transmission, for example. I couple bright states and dark states, and then if I have a Gaussian distribution of disorder, so what was the question exactly there? Okay.
The question is whether what's the line shape of the dark state? So yes, so if it's a Gaussian distribution for the disorder, do you get the Gaussian distribution for the dark state as well? And are there any interesting features in the emission spectrum from the dark state depending on the strength of the disorder?
So the quick answer, I don't know. I didn't do the calculation, but in principle, what we model is that we can get an effective decay. So we can get an effective decay of the bright states into the dark states, which would follow a Laurentian. So would not necessarily follow the Gaussian distribution of the disorder. And regarding the emission spectrum, we didn't calculate it. So that's a good question. I don't know if, depending on the strength of the process, you might either get the Laurentian or the Gaussian, depending on how they are convoluted. So yes, I don't know what the result is going to be, and this is what we would try to calculate.
Oh, okay. It looks like in the, okay. All right, so I guess we still have time for some more questions. So if there are no other questions right now, I'd like to ask a few questions. So also regarding this disorder. So I'm just curious, so how strong in this case, do you know, is the disorder compared to the light matter coupling? Because at least in the experimental spectrum, right, we usually don't see a huge intensities like this at the bare frequency.
so in order to, okay, so in order for the disorder to really break the strong coupling regime, it has to be pretty strong. So it has to be larger than the strong coupling. It has to be larger than the coupling strength. So the analytical estimates show that in principle you can always, no matter how big your disorder is, you almost always get the polaritonic peaks.
Oh, okay.
So they, at least for small disorder, there's almost there's no modification of the polaritons. Right? But the only thing is that, so what's going to happen in this case is that maybe we look at this diagram. So you have a loss rate of A, mode A, you have a loss rate of the bright mode. And the strong coupling condition basically tells you G squared of n is larger than both of these rates, roughly, if they're not close to each other. And what the dark state manifold, so what disorder does, it couples the bright state with the dark state manifold. And if you trace over the dark state manifold, you simply get that B, the bright mode, decays faster than you expect. But as long as it doesn't decay faster than, as long as it's still smaller than G squared of n, you have no problem because you always get strong coupling. So it's, let's say it's pretty resilient to disorder.
And also I have a question regarding the next slide, the fret part. Yeah, so when you wrote the formula for the energy transfer rate in terms of the sum of the Lorentzians.
Yeah.
So in this case, did you strongly couple both the donors and acceptors to the cavity field?
No, this is just the intrinsic fret rate between them without the cavity field participating.
Oh, okay. I see.
So assuming that, so this is actually a perturbative. So when you have the cavity plus the donor acceptor, then actually we looked at one point at the competition between the direct fret, which is mediated just by the electromagnetic vacuum, and then you have indirect fret channels which go through the cavity. And so then, in that case, you are so you can go from the donor to the acceptor, and this is what you say. You just simply go because they are very close to each other. There's a near field. But the other way you can go through the cavity from the donor. So you go to the cavity mode, and the cavity mode interacts with the acceptor. Right? And then you always have a competition between these two paths. So this one would be the normal kappa that we calculate here. This one is here. And the cavity one would be, in principle, is usually much smaller unless you do this this special thing that, for example, is in the experiment by Thomas Everson, where he manages to pump a system, a donor acceptor system inside the cavity through the middle polariton. And then the resonance conditions are in such a way that you do most of the transfer through the cavity. But in our case, again, we don't have this channel, and we only have this direct channel donor acceptor. So the cavity does not participate in this for this expression.
Thank you. So let's see. We don't have any more questions, and it's already about 10 minutes past 10 a.m. PST. So let's end the talk. So again, please join me in thanking Dr. Claudiu Genes for this wonderful talk. And now, before we finish up, I'd like to share my screens and make some final announcements. All right, so I'd like to announce next week's talk given by Professor Javier Esparua from the Center of Materials Physics. Remember to register. It's at the same time, 9 a.m. Pacific Standard Time. And the title is Addressing Atomic Scale Resolution and Nonlinear Effects in Plasma-Enhanced Electrospectroscopy. Finally, I'd like to remind you that the voting for the second postdoc spotlight on Wednesday, August 19th, 9 a.m. Pacific Standard Time. The voting will be sent out today, right? So keep an eye out in your email and social media. And again, thank you and have a great rest of the week. Bye.
Thank you.
All right, thank you.